Whoa! What are you working on? Is that a rover? It looks different.
Yep, but just not any rover. I'm designing a search and rescue rover for interplanetary missions, for rescuing astronauts on Mars or the Moon.
A rescue mission. Is space really that dangerous, like dangerous enough to send a whole rescue unit?
Very much so. Imagine a civilian gets lost and falls into a crater, and then they run out of oxygen. We can't just send a normal rover. We need something that is fast, stable, and smart enough to operate on its own.
Oh, fair enough. But has something like that ever actually happened?
Not yet, but this is about risk mitigation. We face plenty of challenges as space exploration has continued to grow. I even heard that space tour has become a thing, such that of Katy Perry's. And as space exploration grows, risk follows.
You're right. And I don't think we have anything like interplanetary rescue rover before. How about we go over the design together? Maybe I can help out.
Sure, that'd be great. After understanding the urgency and the challenges we face, it's not just about dreaming about the future, but it's also about starting to make it come true.
Now, let us show you how this innovation was designed to address the critical challenge of space exploration.
Let's start from the top. We're using shape memory alloy wheels. No air, super durable, and they bounce back after impact. With adaptive suspension, it handles rough terrain easily.
Slopes, rocks, craters, no problem, right? What about navigation?
Satellite input for location, then onboard AI plans the safest route using optical, thermal cameras, and LiDAR.
Nice. But what if is stuck?
Mm, an automated winch pulls them out. If that fails, we send a rescue drone, flexible arms, guided hook, and an inflatable stretcher.
Then into the evacuation capsule?
Yep, full life support and vitals monitoring. Medical AI will kick in if anything goes wrong.
Now, I will explain about the science principle that we use for our system at our rover. The first system is winch control and automatic hook. First is momentum and rotational motion. We use IMU or inertial measurement unit and torque control to prevent rope slippage or excessive rotation when the rope is pulling the astronaut. Second is friction and grip force. The winch motor is tuned for precise torque control to ensure smooth lifting for the astronaut. The second system is energy and thermal management system. There are three principles. The first is conservation of energy. The entire system is energy efficient. Solar panel input is directed to batteries with minimal loss. The second is conversion efficiency. Gallium arsenide is used for its high solar energy conversion efficiency. The last is heat transfer, a combination of conductive system and multi-layer insulation shielding maintain stable temperatures. The last system is automatic first aid system. Is minimum torque. Arm actuators use controlled force to ensure astronaut safety during movement and treatment.
In our rover, there are three noteworthy mathematical concepts. Let's begin with how it navigates. Once a distress signal is received, satellites calculate the victim's global coordinate. These are then converted into local Cartesian coordinates for simpler and real-time calculations. Using this formula, we'll calculate the straight line distance. For example, if the astronaut is located at 180 meters north and 25 meters east, the Euclidean distance is calculated with the Cartesian distance formula. These are then used to estimate the travel time between the rover and the astronaut. And then, since the terrain isn't flat, the map of Mars can be divided into grids, with each tile having a different cost depending on its risk. The onboard AI will then use a pathfinding algorithm called A-star to avoid high-cost paths and pick the shortest and safest route. Every movement on Mars or the Moon has an energy cost. But the question is, how much total energy is needed for a rescue mission. Here is the table that contains the estimated energy consumption. The data is assumed from the parts that each system used. From this, we can calculate the average consumption to be at around 0.36 kilowatt-hour total for the rescue mission. To ensure safety, the battery capacity should be at around 720 watts. Next, we size the solar panel. On Mars, sunlight is only efficiently available for around 6 hours per sol, or Martian days. We can assume that a 1 meter square solar panel could generate around 1000 watt per day. This means a single 1 meter square panel could meet the mission's energy demand. Lastly, our rescue rover includes a mini medical bay, which is powered by AI. It collects biometric data straight from the astronaut suits. The AI will then apply trends, threshold, and rate of change. For example, if SpO2 or blood saturation percentage drops below 90%, oxygen is applied. If it drops below 85%, the system will then increase flow from 2 liters per minute up to 6 liters per minute.
Two extraordinary judges. We know you have seen many ideas today, but allow us to leave you with one thing: the belief that science can bring hope to life.
We are not just building a miniature. We are building the dream of humanity to survive and thrive. Perhaps the next question isn't what will happen, but what will we do to make it a reality? My name is Bimo.
And my name is Azhar. See you at the final.